Welcome to the deep dive. We're diving into a physics theory today that's causing a bit of a stir.
Yeah.
It's called ECE theory, or Einstein-Cartan-Evans theory.
Right.
And it's really questioning some of the fundamental ideas in physics.
Yeah, that's right.
Things like electromagnetism, gravity,
Mm-hmm.
even the origin and evolution of the universe.
That's right. What's really interesting about ECE theory is how bold it is.
Oh,
It
yeah.
doesn't just try to tweak existing models.
Mhm.
It proposes a total overhaul.
Right.
It even calls itself the post-Einstein paradigm shift.
Wow. So we've got excerpts here from a core document that
Yeah.
lays out the foundation of EC theory. And just skimming through it, I was hooked by the claim that it
Yeah.
derives all the major physics equations from just two structure equations and identities in Cartan geometry.
Yeah, their argument is that the universe at its core is governed by geometry,
Right.
and that Cartan geometry, with its inclusion of both curvature and torsion, provides a more complete picture than the Riemannian geometry that's used in standard physics.
So we've been using the wrong geometry.
Well, they would say that, yes,
Okay.
Einstein's famous field equation, for example,
Right.
a cornerstone of general relativity, only considers curvature.
Okay.
So it's potentially missing a vital piece of the puzzle.
So it's like we've been trying to solve this really complex equation with half the variables missing.
That's a great way to put it.
And ECE theory is saying, hey, we found the missing variables.
That's right. And one of the most fascinating things about ECE theory is its redefinition of electromagnetism.
Oh, okay.
It proposes that the electromagnetic field isn't what we thought it was.
Hmm.
And get this, it suggests that photons, the particles of light, actually have mass.
Hold on, massive photons. Isn't that a huge no-no in standard physics?
You're absolutely right.
Yeah.
So that's why this claim is so controversial.
Right.
But ECE theory points to experimental evidence like the Inverse-Faraday effect,
Okay.
where circularly polarized light induces a magnetic field in a material.
Right.
They argue that this can't be explained unless photons have mass.
Okay, so they're not just throwing out wild ideas, they're connecting it to actual experiments.
Exactly.
But how does a photon with mass change our understanding of electromagnetism? I mean, light still seems to travel at the speed of light, right?
Excellent question. This is where ECE theory introduces the concept of the B3 field.
The B3 field.
Yeah, a longitudinal component of the electromagnetic field
Okay.
that standard models don't include.
Mm-hmm.
This B3 field, according to ECE theory, is generated by those massive photons.
Oh, okay.
And it's what accounts for those unexplained magnetic effects.
So our current understanding of electromagnetism,
Right.
as neatly packaged in Maxwell's equations,
Mhm.
might be incomplete.
That's what they're saying. And
Yes.
it could have big implications.
Yeah, what does this mean for all the technology that's based on those equations?
Right.
And what about other fundamental concepts like the Higgs boson, which is supposed to give particles their mass? How does that fit into a world with massive photons?
Those are all great questions that ECE theory raises. And it's part of the reason why it's so thought-provoking.
Definitely. If it's validated, it could rewrite the textbooks on physics,
Absolutely.
impacting everything from our understanding of fundamental forces to the very nature of light and energy.
It really could.
Mind-blowing. Okay, so we've got massive photons and a mysterious B3 field. What else does ECE theory bring to the table?
See, I noticed something here about Beltrami fields.
Beltrami fields, what are those and why are they important in this theory?
Beltrami fields are vector fields, where the curl of the field is proportional to the field itself.
Okay.
They show up in different areas of physics, but ECE theory uses them to model key phenomena like magnetic flux density
Mm-hmm.
and something called the Parton structure of elementary particles.
Wait, so they're using these fields to peer into the very heart of matter.
Exactly.
What exactly is Parton structure? It sounds like they're going beyond protons, neutrons, and electrons.
They are. They're suggesting that even elementary particles have an internal structure, a distribution of charge and mass that they call the Parton structure.
Wow.
And they believe Beltrami fields can help us visualize and understand this structure.
So instead of tiny billiard balls, we're talking about intricate patterns of energy and charge within these particles.
Yeah, it gets really interesting.
This is getting more fascinating by the minute. What else is hidden in these excerpts?
Well, there's another concept that really captured my attention: spin connection resonance.
Spin connection resonance. That sounds intense.
It is. This is where things get particularly mind-boggling.
Okay. I'm intrigued.
Imagine extracting energy from space-time itself.
Wait, are we talking about free energy here? Perpetual motion machines? This sounds like something out of science fiction.
It does, doesn't it?
Yeah.
But ECE theory suggests it's possible.
Hmm.
They claim that spin connection resonance, a phenomenon arising from the interaction of the spin connection with electromagnetic fields,
Okay.
could allow us to tap into the fabric of space-time as a source of energy.
Okay. I'm officially on the edge of my seat. They have to have some evidence for this, right? It's not just theoretical speculation.
They point to something called the Alex Hill resonance peak,
Okay.
which defied explanation using traditional theories. ECE theorists believe this peak is evidence of spin connection resonance in action.
So we might have already glimpsed this phenomenon in the lab.
That's what they're saying.
This is incredible. But how does this spin connection resonance actually work? And how does it even connect to those massive photons in the B3 field we talked about earlier?
That's where things get really interesting.
Okay, lay it on me.
To understand spin connection resonance, we need to dive a little deeper into how ECE theory challenges the foundations of physics as we know them.
All right, let's do it.
And that leads us to their explanation of LENR,
Eleanor.
or low-energy nuclear reactions.
Right, that's the idea of achieving nuclear fusion at room temperature, right?
Exactly.
Something that's been considered the holy grail of energy production for decades.
It has been. And ECE theory offers a unique explanation for how it might be possible. Again, involving that B3 field.
Yeah.
It's all starting to connect, isn't it?
It is, but before we dive into the world of LENR and how ECE theory reimagines nuclear reactions, let's take a quick break to let all this sink in. We've covered a lot of ground already, from massive photons to the B3 field, from Beltrami fields to spin connection resonance.
It's a lot to take in.
We'll be back in a moment to continue our deep dive into ECE theory, so stay tuned.
Sounds good. So where were we? Oh yeah, LENR.
Right, fusion at room temperature. Sign me up. But how does this B3 field make that happen? I thought we needed like the crazy temperatures and pressures of the star's core to fuse atoms together.
Right, that's the usual thinking.
Yeah.
Remember, ECE theory throws out the rule book.
Okay.
It suggests that those massive photons and their B3 field can interact with the spin of atomic nuclei.
Okay.
Think of it like a subtle dance between these fundamental components where the B3 field kind of nudges the nuclei into a more energetic state, effectively increasing their mass.
So instead of brute force, it's more like a delicate ballet of forces that leads to fusion.
That's a really nice way to visualize it.
I like that.
Yeah.
But doesn't adding mass to a nucleus require a lot of energy? Where does that energy come from?
That's where the mind-bending concept of spin connection resonance comes in.
Okay, back to that.
ECE theory suggests that this resonance can occur within the nucleus, acting like a tiny energy pump,
Okay.
drawing energy from the very fabric of space-time
Oh,
and transferring it to the nucleus, increasing its mass.
so it's like the B3 field is a key that unlocks this hidden energy source within space-time, allowing for a LENR to occur.
That's the idea.
This theory is getting more and more intriguing. But I have to ask, how does the scientific community view all this? Are they on board with these radical ideas?
Well, let's be honest. These are radical claims.
Yeah.
And ECE theory has its share of critics.
Right.
Some physicists argue that the theory lacks mathematical rigor
Okay.
and hasn't been formulated as precisely as standard models. Others point to the lack of independent experimental verification for some of its key predictions.
So it's like they're building a skyscraper with a foundation that some people think might be shaky.
That's a good analogy.
Yeah.
And this criticism of mathematical consistency is a serious one.
Yeah.
Critics also argue that those experimental anomalies, like the Alex Hill resonance peak,
Right.
might have other explanations that don't require such a drastic overhaul of physics.
Right. Extraordinary claims require extraordinary evidence.
They do.
But even if ECE theory doesn't turn out to be the final word, it's sparking a lot of fascinating conversations and pushing the boundaries of scientific thought.
Absolutely. It's forcing physicists to re-examine their assumptions
Right.
and to consider new possibilities.
It's like shining a light on unexplored corners of the universe,
Yeah,
even if that light comes from a source that some consider unconventional.
I like that analogy.
So let's say for a moment that some of these predictions like photon mass or spin connection resonance are confirmed. What would that mean for our understanding of the universe? What kind of world would we live in?
That's the exciting part. Think about the implications of being able to tap into the energy of space-time.
Oh, wow.
Imagine the clean, sustainable energy we could generate if we could harness spin connection resonance.
It would be revolutionary. No more fossil fuels, no more dependence on limited resources.
Exactly.
It would change everything. But even beyond the practical applications, what about our fundamental understanding of the universe?
If ECE theory is right, it suggests that the universe is far more interconnected and dynamic than we ever imagined.
Right.
We might be living in a universe where energy is constantly flowing through unseen dimensions, and where even seemingly empty space is teeming with potential.
That's mind-blowing. It makes me think of those ancient philosophies that talked about a universal life force or cosmic energy.
Right.
Maybe they were onto something after all.
Perhaps. But let's not get too carried away with speculation. We need to stay grounded in the scientific process and continue to test and refine these ideas.
Right back to the evidence. Speaking of which, I'm curious about their claims regarding the cosmological redshift and the expansion of the universe.
Yeah.
They suggest that a finite photon mass could explain the redshift without the need for an expanding universe. How does that work?
They propose that massive photons lose energy as they travel vast cosmic distances.
Okay.
And this loss of energy manifests as a decrease in frequency, which we observe as a redshift.
So instead of space itself stretching and carrying galaxies away from each other,
Right.
they're saying it's the photons that are losing steam along the way.
That's a simplified way to think about it. But it raises a big question.
Yeah, what's that?
If the universe isn't expanding, then what about the Big Bang?
Right.
How does ECE theory explain the origin of the universe?
Excellent point. And what about those enigmatic black holes? Do they ever exist in an ECE universe?
Well, ECE theory rejects the idea of singularities,
Ah.
those infinitely dense points at the center of black holes, arguing that they are mathematical artifacts arising from the neglect of torsion in Einstein's equations.
So instead of bottomless pits in space-time, what are they proposing? Super dense objects, something else entirely?
The excerpts we have don't really go into the specifics of their alternative explanation for black holes,
Okay.
but they do suggest that a universe with torsion could allow for objects to be incredibly dense without collapsing into singularities. It's almost as if the torsion acts like a kind of internal pressure preventing the complete collapse of matter.
Okay, so the universe might be full of super dense objects that are not black holes.
That's what they seem to be suggesting.
That's definitely a new image to ponder. But if the universe isn't expanding and black holes might not exist as we think they do, what does that mean for our overall picture of the cosmos?
That's the beauty of ECE theory. It challenges us to reimagine everything we thought we knew about the universe.
I like that.
It suggests a universe that is fundamentally different, a universe where geometry plays a more active role, a universe where energy might be tapped from the fabric of space-time itself.
And a universe where even those tiny building blocks of matter, those elementary particles, might have a hidden complexity that we're just beginning to glimpse.
Exactly. It's like we've been looking at the universe through a narrow window, and ECE theory is throwing open the doors and inviting us to explore a vast, uncharted territory.
That's a fantastic way to put it. But before we get lost in the wonder of it all, I want to come back to those criticisms we talked about earlier.
Okay.
The mathematical consistency of ECE theory seems to be a major sticking point for many physicists.
It is.
How do proponents of the theory address those concerns?
They acknowledge that the mathematical formulation of the theory is still evolving,
Okay.
but they maintain that the core principles are sound and that the predictions align with experimental evidence.
So it's like they're saying, we're still working on the fine print, but the overall message is clear.
That's one way to look at it. Ultimately, the scientific community will judge ECE theory based on its ability to make accurate, testable predictions that can be independently verified.
Right. The universe has the final say. But even if ECE theory doesn't turn out to be the ultimate theory of everything, it's already accomplished something remarkable. It's shaken the foundations of physics and forced us to think outside the box.
I completely agree. And that's the power of a truly bold theory.
Right.
It challenges us to re-examine our assumptions and to push the boundaries of our understanding.
Speaking of pushing boundaries, I want to delve deeper into one of their more radical claims.
Okay.
The assertion that the equivalence principle, one of the cornerstones of general relativity, actually arises from these anti-symmetry laws they talk about. It's like they're saying that Einstein's brilliant insight has an even deeper root in the fabric of space-time itself.
It is a fascinating proposition. Remember, the equivalence principle states that gravity and acceleration are indistinguishable. Einstein used this principle to develop his theory of general relativity, which describes gravity as a curvature of space-time.
Right. The famous analogy of a bowling ball on a trampoline. warping the fabric, creating a gravity well that pulls in smaller objects.
Exactly. But ECE theory goes a step further,
Okay.
suggesting that the equivalence principle itself emerges from the fundamental geometry of space-time,
Oh, wow.
specifically from those anti-symmetry laws that arise when you include torsion in the equations.
So instead of gravity being a fundamental force or a curvature of space-time, it's more like a consequence of the way space-time itself is structured.
That's a good way to think about it.
It's like the universe is playing a cosmic game of Tetris, and those anti-symmetry laws are the rules that govern how the pieces fit together.
That's a great analogy. And this is where ECE theory gets really interesting.
Yeah.
They're not just tweaking existing models, they're proposing a fundamental shift in our understanding of how the universe works.
Okay, I need a moment to let all this sink in. We've journeyed through a universe with massive photons, a mysterious B3 field fusion at room temperature, a reinterpretation of gravity, and a potential new energy source hidden within space-time itself. And we've only just scratched the surface of ECE theory. I'm curious what other mind-bending ideas lie ahead.
Well, there's one more area that ECE theory boldly tackles.
Okay, hit me with it.
The very nature of the fundamental forces of nature.
Okay.
They claim their theory can unify gravity, electromagnetism, and even the weak and strong nuclear forces.
Wow.
Imagine that one framework to explain all the forces that govern the universe.
Okay, you've got my attention again. This is getting too good to miss. But before we get lost in a unified field theory, let's take a quick break to gather our thoughts and prepare for the grand finale of our deep dive into ECE theory.
Sounds good.
We'll be back in a moment to see how this theory attempts to tie it all together. So we're back and ready to tackle this idea of a unified theory of everything.
All right, let's do it.
From ECE theory.
ECE theory claims that it can unify gravity, electromagnetism, even the weak and strong nuclear forces.
That's a tall order. Unifying the forces has been like a holy grail of physics for centuries.
It has been.
How do they even begin to approach something so ambitious?
Well, they believe the key lies in Cartan geometry, the mathematical framework that underpins ECE theory.
Okay.
Remember, this geometry includes both curvature and torsion,
Right.
unlike the Riemannian geometry used in standard physics.
Right. It seems like that extra dimension of torsion is key to a lot of ECE theory's unique predictions.
Exactly. ECE theory argues that by fully embracing Cartan geometry,
Okay.
we can see those seemingly separate forces as different aspects of the same fundamental reality.
So gravity, electromagnetism, the nuclear forces, it's all connected.
That's what they're saying. Think of it like looking at a tapestry from different angles.
Okay.
From one perspective, you might see a flower.
Right.
From another, bird. From yet another, a geometric pattern.
Okay.
That's all the same tapestry.
So they're saying that gravity, electromagnetism, and the nuclear forces are like different patterns woven into the fabric of space-time.
Exactly.
And Cartan geometry gives us the tools to see the whole picture.
Precisely. It's a pretty elegant vision.
It is. But like with anything in ECE theory, it comes with challenges and criticisms.
Of course, unifying the forces has stumped some of the brightest minds in history.
Yeah, for sure.
So there's definitely some healthy skepticism out there.
Right. What are some of the main hurdles that ECE theory faces in trying to unify the forces?
One of the biggest challenges is developing a mathematically rigorous and consistent framework that can accommodate all the complexities of these forces. Critics argue that ECE theory as it stands lacks the mathematical precision and predictive power to truly unify the forces.
It's like they've sketched out a beautiful blueprint, but they haven't quite figured out all the engineering details yet.
Yeah, that's a good way to put it. Another challenge is reconciling ECE theory's predictions with the huge amount of experimental data we already have.
Right. The standard model of particle physics, even with its limitations, has been incredibly successful in explaining and predicting a wide range of phenomena.
That's true.
So it's not enough to just have an elegant theory. It has to match up with what we actually observe.
Exactly. That's the heart of the scientific process.
Right.
To gain wider acceptance. ECE theory needs to show that its predictions can be tested and verified experimentally.
So the universe has the final say.
It does.
But even if ECE theory isn't the ultimate theory of everything, it's already done something pretty remarkable.
What's that?
It's shaken things up in physics and forced us to think outside the box.
I agree. It suggests that the universe is fundamentally geometric in nature.
Yeah.
That energy might be tapped from the fabric of space-time itself.
Right.
And that even the most basic building blocks of matter have a hidden complexity. that
Wow.
we're only just starting to understand.
It's like we've been looking at this black and white photograph, and ECE theory is suddenly revealing this vibrant, multidimensional world in full color.
That's a beautiful way to put it. It definitely sparks the imagination and opens up a whole new realm of possibilities.
So we've explored some pretty mind-bending concepts today.
We have.
From massive photons to spin connection resonance, from LNR to this idea of a unified field theory based on Cartan geometry. It's been a wild ride through the world of ECE theory.
It really has. Even
Yeah.
if some of these ideas don't hold up over time, ECE theory has pushed the boundaries of what we think we know
Yeah.
and challenged us to really question our assumptions about the universe.
And that's what makes science so exciting.
Absolutely.
The constant exploration, the questioning, the pursuit of knowledge that takes us beyond what we're familiar with and into these uncharted territories.
Well said. Who knows, maybe someday we'll look back at ECE theory as a crucial step on the path to a deeper understanding of the universe.
It's definitely given us a lot to think about. And to all our listeners out there, keep your minds open, your curiosity piqued, and never lose that sense of wonder. There's a whole universe out there waiting to be explored.
Thanks for listening, everyone.